I see infinity, correct?
Yes.
X sine pi divided by x. Okay? Very good. Good pick. So when x approaches infinity, this will approach. Perfect. And this will approach. Let's do this pi over 6 first. Pi over x first. So pi over x, so as x approaches infinity, pi over x will approach.
0.
Yes, sine 0 is
0.
0. So this is one of the 7 indeterminate cases, which is 0 times infinity. Good. So I have to manipulate this function somehow. I have to present it in such a way that hopefully I can change it into 0 over 0 or infinity over infinity. I will never take sine anywhere. Sine has to stay where it is, because if I bring it somehow to the denominator and say 1 over sine to negative 1, I will never get out of that. So sine is not a function that can be manipulated in this kind of limit. So my only hope is, what should I do with x? So maybe x can help, and then sine pi over x over 1 over x. So instead of having x, I change it into 1 over x, which is the same thing. So when you flip 1 over x, you get x.
Now, in this case, since that's an indeterminate form, why can't we use L'Hopital's rule to get?
An indeterminate case in which I can use L'Hopital's rule are only 2. Either infinity over infinity or 0 over 0. This is not an indeterminate case in which I'm allowed to apply L'Hopital's rule.
Okay.
Good question. So now, is this clear that this function, I would like you to say yes or no. Is this clear why this function is the same with this function? We understand that? Okay, now let's try again. I know that the top approaches 0. What about the denominator? 0. Now I'm ready to apply L'Hopital's rule. In this case, I can. And it was just a simple algebraic manipulation. I did not change the function. I changed the outlook of the function. No. Okay, so then I have limit as x approaches infinity. I differentiate the top. I differentiate the bottom. This is one of the situations in which, if you remember, I said, please remember, if you can, the derivative of 1 over x. Super important. What is the derivative of 1 over x?
Minus 1 over x squared.
Excellent. So now I differentiate the top. Sine prime is cosine pi over x times the inner function prime, not to be confused with that angle times whatever. So let's put cosine separate, and times the inner function prime. Again, the same thing with pi in front. So pi is a constant, and I have to differentiate 1 over x, which gives us the same thing, negative 1 over x squared. Of course, I will simplify the function, removing this and removing this because they are the same. So now I'm trying to calculate the limit as x approaches infinity. Pi in front, you can put it in front of the limit or just in front of the function. It doesn't matter right now. So where does pi over x go when x approaches infinity? Careful. Pi over x when x approaches infinity goes to 0. And cosine 0 is 1. So this approaches 1. So then the answer is pi. Very good. Excellent. Well done. Very good question. Anything else?
45.
Yes. Same page? Very good. 45. 45, 44, 45. I see it. So limit as x approaches infinity, and we have x to the third times e to negative x squared, correct? Yes? Perfect. So we take it piece by piece. When x approaches infinity, x to the third will approach Perfect. So now, again, piece by piece, when x approaches infinity, x squared approaches, and negative, it's going to be negative infinity, right? So when x approaches infinity, this piece will approach negative infinity. And I have e to negative infinity. I shouldn't write this, it's not legitimate, but I will write it to explain. So e to infinity, negative infinity is 1 over e to infinity. Where does this go? Yes. So I am back to the same situation. The same indeterminate case, 0 times infinity. Now, if you remember those 7 indeterminate cases, the most difficult ones to work with are the power ones. This one, and this one. These are the most difficult. This one is not as difficult, and this one is okay. But these are the power ones are the most difficult. Okay, so I have infinity times 0. I will not move x cubed anywhere because it's okay where it is, but I will move this one, which is e to a negative power, to the denominator, because I can. I'm allowed to do that. So this is x to the 3rd over e to x squared. So that's one of the reasons in general where we like not having negative leading powers in an expression. So that's pretty much it. I go again and plug in infinity, and I realize that the numerator is still going to infinity, and the denominator by itself, now it's going to yes. Therefore, I change the infinity times 0 or 0 times infinity into one of the 2 cases in which I can apply L'Hopital's rule. So now I'm happy. I will write limit as x approaches infinity. The top is what is the derivative of the top? Very good. And the derivative of the denominator? Very good. Perfect. So now let's see what we have. I will simplify an x, and then what? I will take 3/2 in front. That's a constant. I don't want to bother with it. So this is limit. This is one of the limit laws. So I have x squared over, I'm sorry, I already said that and I didn't do it. So I have x at the top and e to x squared in the denominator, and 3/2 outside. Then what? I check again whether I'm done. But the numerator approaches and the denominator approaches infinity. E to infinity is infinity. So then I have 3 over 2. I differentiate now the top. So the top is 1 and the bottom is e to x squared times 2x. Now the numerator is 1. This is no longer L'Hopital's rule. The numerator is 1 and the denominator approaches infinity. And 1 over infinity is how much is 1 over infinity? 0. And 0 times 3/2 is 0. Very good. Good question. Anything else? Yes?
In this situation, if we would have just left the 3/2 in, like, on the other side of the limit, is that okay?
Of course, it's the same thing.
Okay.
However, it's in the way.
Okay.
I don't want to differentiate it with the number in there. I make my life even more difficult.
Yeah.
It's a constant, and this I'm allowed to remove and put a constant in front. It's by one of the limit laws. If you remember, and even the derivatives are allowed to do that. Even in a derivative, I'm allowed to do the same thing. So let's refresh our memory on this. So limit of a constant times a function as x approaches a is c times the limit of the function as s approaches a. That's the rule I used. Or c times f, for that matter, just another example, is c times f prime. We want to make it as simple as possible. Very good. Good questions. Anything else? Is there anything else you worked on? Other questions? Is there anything else?
37 on page 317.
317, 37. Okay. 37. 37 on 317. Very good. 37. 37. I see it. Okay, so we have y equals 1/2 x minus sine x. And they want everything between 0 and 3 pi. I think it's not closed. No, it's open. Sorry. And the question is, do everything. Exactly how I asked you to do this, right? Are you going to turn this in today? Okay, perfect. Okay, so I get my chart going. So I'm going to call this f of x. So f prime, f of x, and the second derivative. I'm given 0 to 3 pi. There is no discussion there. For some reason, it's given open, so I can't use any of this. So I have to consider that this is undefined at 0 and undefined at 3 pi. I don't know why they consider that, but that's what the problem is giving us. On the interval 0 to 3 pi, but not 0 and not 3 pi. So I can include those. Okay, very good. So I will start with studying the sign. So if I put 0 in here, then I get 0. So there is no asymptote or limit that needs to be determined in there. If I put 3 pi, so 3 pi is on the left. So this is 1 pi, 2 pi, 3 pi is right here. Again, sine is 0 there. But this will be 3 pi over 2 right here. Will be an open point. The open point will be 0, 0, and the other open point will be 3 pi, 3 pi over 2. It will be an open point because they decided, for whatever reason, not to allow us to include 0 and 3 pi. Okay. So all I have to determine here, there are no limits, no asymptotes, nothing, but I have to determine when this function is 0. Okay? So we want to find the X Intercept, which is solving this equation. Yes, I can solve it with the graphing calculator because there is no way I can do this by hand. Or, since it's an excellent example of what follows today, which is this, we can put this problem on hold for a few minutes till I explain the method, and then we'll find the solutions as an application of Newton's method. And then we'll go back and we'll finish the problem. Is that okay? And I know we still have to work on a lot of optimization problems, as I promised, and we'll choose as many as we can. Okay, so I cannot do this by hand, algebraically. There is no method for this. So we still want to solve the equation, and we don't want to use a calculator. Because if we use a calculator, then we will be able to find the solution by simply finding the zeros or finding the intercepts with y equals 0 and this other function. That's not a problem, no brainer. So I'm going to put this aside. I'm going to talk about Newton's method, and we'll come back. It's a perfect, perfect example. Okay. I probably, in Newton's method, I probably have something very similar to that. Here it is. 1/3 x equals sine x. Because no one can solve this by hand. Okay? Very similar. Good. So let's take a look at the following graph. Let's say I'm using the intermediate value theorem. I have a function, and I know that between this and this, let's say between 2 and 3, there is a solution. By the intermediate value theorem, this is a continuous function. It changes sign, so it does this. It's continuous, it's negative at 2, it's positive at 3, so there must be a solution here. We would like to call this solution R. It doesn't, the notation is not important. So using the intermediate value theorem, we know there is a solution between 2 and 3. We will have to use at least, the maximum unit interval. We are not going to say the solution is between 0 and 5. No. We have to have it at maximum 1 unit interval. So I established that there is a solution between 2 and 3. Okay. I will have to start with an initial value, normally denoted by x0, initial value. And let's suppose that I choose the initial value that I want to start with, x equals 3. x0 equals 3. So I choose to start with x equals 3 because I want to start with 3. I'm not going to start with 10. I'm not going to start with negative 3. I will either start with 2 or with 3. Oh, this time I chose 3. Very good. So then I know this point has the following coordinates. Definitely 3 and definitely very good. Okay, so next step, I'm going to draw the tangent to the graph. So let's say this is the tangent. It does not hit here. It's just they're so close. So I'm going to say this is the tangent. Can anyone give us the slope of this tangent? It's at the point. Say it again. Of course. Good. And as you notice, I extended the line, the tangent line, till this point. I'm going to call this point x1, comma 0. I don't have it. I don't know what x1 is. But I know that it's on the x-axis, so this point must be x1, comma 0. Agreed so far? Okay, perfect. Stay with me, please. Now, what does x0 mean? This is my first approximation of the solution. It's a huge error, right? If I say that the solution is 3, I will be making a huge error. But I will say this is x equals 0 is my initial value as an initial approximation of the solution. Huge error. But now I'm telling you that x1 is a much better approximation of R. Would you agree with me? 3 was very far from R, but x1 is much closer to R than 3 was. So I'm getting closer to the real solution. Would you agree? Yes? Okay. I would like to determine x1. So that's my target right now. I want to find x1, which is a better approximation of R than x0 was. Okay. So I have 2 points and the slope of this line. Which 2 points? I have this point, which is 3 comma f of 3. And I have this point, which is x1 comma 0. And I have the slope of the line, which is f prime of 3. Having 2 points and the slope of the line, I can determine the equation. Or what is really needed at this point is to simply write that f prime of 3 equals f2 minus f1. I don't need the f, just 0. Or y2 minus y1, which is f of 3 minus 0, over 3 minus x1. Would you agree? So the slope of this line is determined in two ways, by f prime of 3 or f y2 minus y1 over x2 minus x1. From this equation, what do you think I am going to determine? What I'm after. The better approximation of the real solution R. So I'm definitely after x1. All the rest is given now. I have all the rest because I have the function. Once I have the function, I have f of 3, I have f prime of 3. There are no unknowns here other than x1. And x1, after I'm done, I will say, and I hope you would agree, that x1 is a better approximation of R than 3 was for R. And this is called my first iteration. x1, first step if you want, or first iteration. So let's determine x1. I will cross multiply. So f of 3 equals f prime of 3 times 3 minus x1. I will divide both sides by f prime of 3. So I have 3 minus x1 equals f of 3 over f prime of 3. I will move 3 to the other side. And then I will multiply both sides by -1. I hope you agree that once I have x1, I have a better approximation of the solution, the real solution R. Okay, stay with me. So I have the situation now. This is R. This is x1. I will repeat the process. Can anyone give us the coordinates of this point? Definitely x1, comma, of course, thank you. Of course, I will continue with the tangent at that point. Can anyone give us the slope of the tangent at this point now?
f prime of x1.
Very good. Excellent. I have determined another point here, which now is x2 comma 0. How do you think x2 is called? Would you agree that x2 is even a better approximation of R than x1 was? Okay, so then I have 2 points. I have this point x1 comma f of x1, and I have this point which is x2 comma 0, and I have the slope. So f prime of x1 will be f of x1 minus 0 divided by x1 minus x2. What am I after now?
x2.
of course. Now from this, without any calculations, can you give me what x2 will equal to? And then I'm going to ask you about x3. So look at this, and please tell me, what do you think x2, without any calculations, can you deduce anything there? This was my initial value. This is x1. So this is x sub 0. This is x sub 0. This is x sub 0. Those are all three, right? From the initial value that I picked. What do you think x2 will equal to? x1 minus f of x1 over f prime of x1. Now I would like you to come up with x3, the third iteration, which will be even closer to r than x2 was. Can anyone come up with x3?
Minus x over prime of x.
This is Newton's method. And we can go and continue forever. So if I ask now xn plus first, the n plus first iteration, what would you say? What will that equal to?
N minus f of x and
That's it. There are two potential problems here. And the two potential problems are are related to x0 as the initial value. What could go wrong? If I pick an x0 whose derivative at 0 is x0 is 0, I won't get anywhere. So that's my first warning. When I pick x0, whatever that number is, I have to make sure that it does not make the derivative 0. That's crucial, because I'm not going to determine anything. I'm not going to even determine the first iteration if f prime of 3 is 0. That's the first caution. The second caution is to make sure, or I should say the method would not converge. Normally this method converges in 3 or 4 steps. You will be able to get as many digits as you want, accuracy for the solution. So the second word of caution is this, and I have them on the handout somewhere, and we'll talk about it in a second. So the second word of caution is this. If you are looking at this solution, and there is a max or a min between the starting point, so if you want to start here, you will never get this solution, because it will all happen here, or will go up and down. You will never get here. So what I'm saying is, the initial value, if you want to determine this solution, you have to make sure there is no max or min between the initial value you pick and the solution you need, because the method will never converge. You will stay here, you will never get here. So two things. The initial value you pick, if the derivative cannot be 0, and the initial value you pick, since you're looking for this solution, you cannot have a max or a min between the initial value and what you're looking for. So these are the two words of caution. Now we are ready to come back here and solve this equation. Okay? So we have f of x equals 1/2 x minus sine x. I just copied it, and I'll come back to this. But we are trying to find the x-intercept, so I have 1/2 x minus sine x equals 0. This is the equation we want to solve, which no one can solve by hand. There is no algebraic method for this. Okay, so this is our function. So we have to start with an initial value that we will pick in a minute after we look at Bless you. It's a continuous function. I will be using the intermediate value theorem to choose an initial value in a minute. And then x1 will be x0 minus f of x0 divided by f prime of x0. And then I'll show you how to put this in the calculator. So now, I have to find the derivative. So f prime of x equals 1/2 minus cosine x So then, if I want to create, you'll see in a minute why I will create a function. If you want to call it something else, I'm going to call it, let's say, uppercase f. Here's the function I create. X minus f of x, which is 1/2 x minus sine x over f prime of x, which is 1/2 minus cosine x. So I created the function coming from Newton's method. And you'll see in a moment why I created that function. But for now, let's find an interval, somewhere between 0 and 3 pi, because I need to find it or choose an initial value. So somewhere between 0 and 3 pi. Why 0 and 3 pi? Because that's what they gave us. Somewhere between 0 and 3 pi. If this function is never 0 between 0 and 3 pi, then there is nothing to find. So between 0 and 3 pi, I'll see where the function is 0. Okay? Not this function. This function. Okay? So let's punch it in y equals, clear. So 1/2 x or 0.5x. And then minus sine x. And I will go to second end table. I will punch in 0. I already see a 0, but I can't really use it because it's not in the domain. I'm going to punch in 1, which is 1 radian. I'm going to punch in 2, which is 2 radian. And I'm done. So I see that for 1 radian, the function is negative, and for 2 radians, the function is positive. So there must be a solution between 1 and 2. Now I'm ready to choose the x0. You can choose 1 for x0, or you can choose 2 for x0 to determine the solution between 1 and 2. Now, if this function has 10 zeros between 0 and 3 pi, it will take a long time. Oh, we'll see. So let's just illustrate the method with one of the two, whichever you want. You want to use x0 equals 1 or x0 equals 2. I'm looking at this. No matter what you choose, cosine 1 radian with minus in front plus 1/2 is not 0. What you cannot choose is pi over 3. If you choose the initial value to be pi over 3, then this is 0 and you cannot do anything. You cannot go not even to the next step. Because cosine pi over 3 is 1/2. 1/2 minus 1/2 will be 0, and this will be 0. So the initial value cannot be pi over 3. So it can be 1 radian or 2 radians for determining the solution between 1 and 2. So which one would you like to start with? What is your initial value? Either 1 or 2 to determine the solution between 1 and 2. Which one? Okay, we want to start with 2. Perfect. So we have the initial value. Here's my next step. I will put in the graphing calculator this function. Exactly how you see it. The x minus the function at the top and the derivative at the bottom. So I'm going to go back to y equals. And I will incorporate this so I don't have to type it in again. So I will insert x and minus and put parentheses because this is the top. I will continue with parentheses again after sine x. parentheses, and divide in parentheses. Now I have 0.5 minus cosine x. 0.5 minus cosine x. Okay? So this is the function, it's not our function. This is the function we created to use in order to determine the solution. I forgot to ask you how many decimal digits you want, and we'll stop for whatever number of digits you want with accuracy for the solution. This is a function we created using Newton's method. This is not the original function, but this is what we need for Newton's method. Okay, so second and quit. Let's get out of there. And now let's go to, clear? Okay, let's go to variables. Y variable, variables, Y variable, enter, call Y1. I don't really want to see this at all. Look at what's happening here. Doesn't matter. Okay, in parentheses, 1, close the parenthesis. And press enter. And let me see my mode. Mode is in radians. When the solution, when x, oh, I'm sorry. So you said 2. I'm sorry. So go back to variables. Variable, and 1, in parentheses, 2. So it's 1.9. Did we expect that? Between 1 and 2? The solution is somewhere between 1 and 2. So I got 1.9. Any questions? Here's what I did. So what is this, by the way? This is x1. x1 equals 1.9009955. Here's how I continue. I continue with second and enter, but I overwrite 2 by the previous answer. I want the calculator now, in this function that is Newton's method, I want the function to be evaluated for 1.9009955 without me having to type it in. And I press enter. I recall the whole thing one more time. Now I don't have to type in anything, because right now the calculator will take in this second iteration, x2, which I see is 1.895511, will plug it in Newton's method, and will give us an even better approximation of the real solution that I'm looking for between 1 and 2. So this will be our third iteration, 1.895494. How many digits do we want? If we only want 3 digits, we're done, because they already repeated themselves. 895, 895. But now if you want 4 digits, then I have to continue. I will redo second and entry and press enter. And now I have 2, 4, 6, 8, 9 digits repeating. So I don't really need to write this again, because the method converged in 3 steps, in 3 iterations. I got a repeat, so I don't need the last one anymore. So this was the initial value, this was x1, this was x2, and this was x3. Any questions? Any questions?
Where in the other calculator?
Which part? So I went to the variables, and then functions to the right, and I called function y1, and I plugged in y1, 2. That's what we decided to start with. So once I got the answer, I recalled y1, but I deleted 2 and put in the previous answer, because I want the calculator automatically to get this in here. then automatically to get this in here. And then automatically get this in here to get this. So I don't have to do anything. Because if I put it in by hand, I would pile up the error. Not too much, but still. So depending on how many digits we want, this is one of the solutions. If you want only 3 digits, one solution is 1.895. Now I have no idea how many solutions does this equation have. Look, it's horrible what's happening here, but I did not put the interval. So between 0, that's correct, and 3 pi, that's what they wanted us to use. I'm going to put a scale of pi. And y minimum, I have no idea. I'm going to put -6 to 6. Actually, I do have an idea. Because x, well, x can be anything. So x between 0 and 10, it's maximum 5 minus 1. So 4, yeah. Okay, so that's okay. So with a scale of 1. So let's see the graph. Oh, of course, I'm sorry. Makes no sense. So this is not the graph I need. This is not the function I need. Stop, stop. This is the function I need. I'm going to de-highlight this. I want to de-highlight that, please. Okay, this is the function I want. 0.5 minus sine x. That's the function I need. Yes.
There is 0.5x minus sine x.
Thank you so much. Yes, of course. Thank you. Very good. So now I want to graph this. So it has 1. Oh, I'm so happy. It only has 1 solution, and we found it. Other than 0, 0, but 0 is not in the domain. So the solution is between 0 and 1. And we found the solution is right here. And this is the only 0 of the function on the interval 0 to 3 pi. That's all I care about. And we use Newton's method. And you can say yes, but you still use the calculator. True. But I did not use a calculator in the sense that I had to rely on the calculator. I can still do some of it by hand. So I can find an approximation. But other than that, the solution with algebraic method would not be possible. Okay, so our solution was 1.895. So 1.895, and this is 0. Good, so now I'm going to look at the first derivative. So f prime of x equals 1/2 minus cosine x. This I know how to solve because this is cosine x equals 1/2, which is between 0 and 3 pi. We have several solutions here. So let's talk about this. So in order to solve cosine x equals 1/2, we have a solution in the first quadrant, a solution in the fourth quadrant. So that's pi, 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 and one more in the first quadrant. So 2 in the first quadrant and 1 in the fourth quadrant. So this, if you remember, we said that this is pi over 3. That's one of them. None in the middle. It's right here. So this is pi over 3. This one must be 2 pi minus pi over 3. 2 pi minus pi over 3. So the one solution is pi over 3. The other one is in the fourth quadrant, 6 minus 1, 5 pi over 3. That's the second one. And there is also a third one, which is pi over 3 plus 2 pi. Pi over 3 plus 2 pi. So this is 7 pi over 3. All these are between 0 and 3 pi. So pi over 3. Now I have to identify if pi over 3 is before 1.895 or after. So yes, it is before. So this is pi over 3 is here. 5 pi over 3, yes, is here. And 7 pi over 3, of course, is here. So 0, 0, 0. This was not an easy problem so far, right? Yes, we wanted to illustrate it with Newton's method, but still. Okay, so now in this function, I need a third function here because I want to study its sign. So I'm going to de-highlight this, and I am going to put in, it's 0.5 minus cosine x. 0.5 minus cosine x. And go to second table. And I'm going to plug in 0 to see the sign to the left of pi over 3. So I see it's negative, so I'm going to put negative here. Then I'm going to plug in 1.895. This is, yes, definitely correct. So 1.895, 1.895, and enter. So it's positive. So, oops. So I'm going to put positive here. Then I'm going to put, this is 2 pi. Okay, so I'm going to put 2 pi. 2 times, just want to make sure that I'm correct. So that is correct, and then 5 times pi divided by 3. I just want to make sure that's correct, yes. And the numbers are in order. Okay, so the next one is 2 pi. 2 times pi, clear. 2 times pi, okay. So it's negative, so I'm going to put negative here. And then I'm going to plug in 3 pi, and most probably see positive. So 3 times pi, yes, positive. Okay, now I have to put in the function, this value, and this value. So I go back to my y equals. I will de-highlight the derivative and highlight the function. So now in the function, I will plug in pi over 3. Pi divided by 3. I will plug in 5 pi over 3. 5 pi divided by 3. And I will plug in 7 pi over 3. 7 pi divided by 3. Okay, so I will write these numbers. Negative 0.3. I will write 3.5. And I will write 2.8. Good. Now, I'll try to make sure, I have to make sure that these two rows work together, because otherwise something is wrong. Okay, so let's do this now. Between 0 and negative 0.3, is the function decreasing according to this? Is it decreasing? The first derivative is negative. Between 0 and negative 0.3, the function is decreasing. Between negative 0.3 and 0, is the function increasing? Is it supported by the first derivative? Good. Between 0 and 3.5, is the function increasing and the derivative works with it? Good. Between 3.5 and 2.8, is the first derivative negative because these numbers are decreasing? And between 2.8 and 3 point something, that's 6 divided by 2, more than 6, okay? So more than 3, the function is increasing. So the two rows work well together. Finally, the second derivative. So when I differentiate this, I have cosine x. 1/2 goes away. Cosine prime is negative sine. With minus in front, I get sine. Okay, I have to find where sine is 0 in the interval 0 to 3 pi. Well, sine is 0 here. Sine is 0 here. Sine is 0 here. Sine is 0 here. So at 0, at pi, I don't know where I'm going to put pi. Okay, there's not enough room in my chart. So at 0, at pi, at 2 pi, and at 3 pi. 0 and 3 pi are disregarded because they're not in the domain. So I have to include pi and 2 pi somewhere. So pi, one more time, what did I get for that? I get 5. Okay, so pi must be in here. And where is 2 pi? Okay, 2 pi is 6 point, and this was 5 pi. So, oh, I already have 2 pi. It's in the middle, right there. Yes, perfect. Okay. I already put it because I used it. Okay, so now this is 0 at pi, and it's 0 at 2 pi, but I have to find these values also. So I have to go back and determine the function at pi and the function at 2 pi. Okay, so 1.57 and 3.1. So 1.57, that's correct, yes, and 3.1. Yes, perfect. So this is definitely an inflection point. I shouldn't say, I have to study the sign before I do that. This is definitely a local min. This is definitely a local max. And this is definitely a local min. Okay? So now I have to study the sign here. No problem. I go back, I create another function, which is right now, I de-highlight everything. So I only need this new function, which is sine x. Okay, go back to second and table. To the left of pi, I'm going to say pi over 2. I get a positive number. So I checked with pi over 2 somewhere here, so it's positive. Then I will check with 5 pi over 3. 5 pi divided by 3, negative. So I write negative. And then I check with 7 pi over 3. And let's see, I'm assuming it's going to be positive. Positive, as expected. So therefore, open upward, downward, upward. Indeed, this is an inflection point, as well as this, because the second derivative changes sign. A problem like this cannot be on a test or a final exam, right? Because it took me, what? I explained the Newton's method, but still. It takes a long time. So it's a very good practice. Once you understand how to do something like this, it's really good. Okay, so we are ready now to graph, finally. We are graphing this function. Okay, so pi, 2 pi, 3 pi, that's all they want. Okay, let's see how high does this function go. 3.5. How low does it go? Negative 0.3. Okay. So I'm going to say 1, 2, 3, 1. Okay. So the function starts at 0, 0, but with an open point. With an open point at 0, 0. It's decreasing, opening upward. Pi over 3 is here. So this is 0 to pi over 2. So pi over 3 is right here. It's negative 0.3. So opening upward, decreasing till this point, which is a local minimum. Then it will cross the x-axis at roughly 1.9. What is 1.9? Where do I, this is 3.14. This is 3.14 over 2. So if this is 3. This is 3. I'm going to say 2 is here. So it opens upward, continues to open upward till it crosses the x-axis, and this is the local min. Then continues to increase till the inflection point at pi is 1.57. 1.57. So continues to increase, opening upward. This is an inflection point. The function changes concavity. It continues to increase to 5 pi over 3. Where is 5 pi over 3? So between 0, I have 0 and pi, I have 3 pi over 3, right? And then I need 2 more. And this, okay, it's beyond that. Okay. So till this point to 3.5. Changes concavity and opens downward, increasing to this local max. 5 pi over 3, comma 3.5. 3.5. Okay. It continues now. It crosses at 2 pi. At 2 pi. What did I write here? What is this? Oh, yeah. So what did I get there? 3 point what? 3 point what was it? 3.1? Okay, wait. Okay, sorry about that. Okay, so at 2 pi, it changes concavity again. It continues to decrease, and at 2 pi is 3.1. So this continues to decrease. Here it has an inflection point again. It will change concavity and go to 7 pi over 3, 2.8. So 2.8, but the problem is, where is 7 pi over 3? I had 5 pi over 3 here. Does it go beyond 3 pi? So that's 2 pi. 2 pi plus pi over 2. 2 pi plus 5 is 5 pi. Yes, it goes beyond that. Okay, so it changes concavity and it comes to a local minimum. And then 3 pi over 2 is roughly 3, right? So it continues to increase. Any questions? So that's our f of x, 1/2 x minus sine x. Tough. A lot of work on this problem. Any questions? Any questions? Thank you for bringing that up.